Welcome to Unit 2 in Topic 2.1. It's titled Change in Arithmetic and Geometric Sequences. This is pronounced arithmetic. It's spelled exactly like the word arithmetic, but it's pronounced arithmetic, just for the future. But we're talking today about sequences, which are different than functions. So a sequence... Ooh, ball break. Apparently I can't spell anything anymore. That feels wrong. Nope, that's right. Sequence. Wow, okay, I'm going to turn my brain on, I promise. A sequence is a function from only the whole numbers to the real numbers, which means we're not going to be using fractions as inputs. We're not going to be using decimals as inputs. We're only going to be using the whole numbers and not actually connecting the dots of these functions. It's a sequence. This means that we are only able to plug in whole numbers into the sequence, but we can get any real number as the output. So our outputs can be fractions, can be decimals, but our inputs are only going to be discrete values of whole numbers. Since they're discrete, they're just going to be dots, not connections. So avoid the temptation to play connect the dots here. This is a discrete function in a sequence, not an actual function like we've been using in other classes. So let's consider the sequence defined by a sub n equal to 4n minus 3. So notice how I said all of that. This is a sub n, sub for subscript. So a sub n is equal to 4n minus 3. It wants me to find a sub 1 and a sub 7. Those subscripts are telling me what to plug in. So a sub 1 is literally telling me to take the number 1 and plug it in where the n was in the equation for the sequence. Right? This is just like function notation, except it's in sequence form, so the number I'm plugging in is a subscript instead of in function notation. Well, 4 times 1 is 4, and 4 minus 3 is 1, so we would say that a sub 1 is 1. Those numbers in the subscripts, again, tell you what to plug in. So if I find a sub 7, what number are you plugging into the function? 7. Easy peasy. So this is 28 minus 3, which is 25. Sound good? That's kind of the basics of the way the notation for sequences is put together. A sub n represents the output, where n is the input. So it still tells you inputs and outputs. It's just a sequence instead of a continuous function. I almost lost. I swear my brain is... I had coffee this morning, I promise. It's just not hitting yet. So in this course, we will study two important types of sequences, our arithmetic sequences and our geometric sequences. Arithmetic sequences actually behave a lot like linear equations or linear functions. So these are going to look very familiar. They're going to look like you want to connect them with a straight line, but we do not because they are not continuous. It's only the whole number, so it's just dots on our screen. Because they behave like linear functions and linear functions have a constant slope, these functions have common differences, which we can think of as the slope, even though there's no line to actually have an incline. But they're going to change at a same value each time. So they have a constant rate of change, where in sequence world we call that a common difference. The formulas, there are two versions for the formula of an arithmetic sequence. The first version is a sub n equal to a sub 0 plus the common difference times n. This is just y equals mx plus b, but with the notation for sequences. Then you have a sub n equal to a sub k plus d times n minus k. That's just point slope form in sequence. Because, if I zoom in so I can write, a sub 0, which is up at the top one, a sub 0 is your initial value, which is just like your y-intercept in a linear function. That's b, a sub 0. D is your common difference. That's like your slope, except it's called a common difference in the world of sequences. And then if we jump down to the bottom, a sub k is any other point. So we're going to call it the kth term because it's the subscript of k, the kth term in the sequence. But that's just another coordinate point, k comma a sub k. So this is y equals b plus mx, slope-intercept form. This is y1, or y equal y1 plus m times x minus x1. It is literally just point, slope, and linear function, but in the world of sequences, so we change the letters. Okay, let's see an example of this in real time. So if we have this sequence, a sub n equal to 3n plus 1, we're going to want to graph this. So just like when we had a regular equation, we want inputs and outputs. So we have to make our own table, or make a table for n and a sub n, which is like x and y in terms of regular functions, but in sequences, we use n and a sub n. And just because I've done this problem before, we're going to plug in 3 numbers. We're going to plug in 0, 1, and 2. Remember, you're not plugging in decimals, you're not plugging in fractions. And if I do that, I'm literally just plugging that in for n. 3 times 0 plus 1 is 1. 3 times 1 plus 1 is 4. And 3 times 2 plus 1 is 7. This will give me just the coordinate points that I need to plot on the graph, and I will resist the urge to connect the dots because it is a sequence of numbers. So I have the coordinate point 0, 1. I have the coordinate point 1, 4. I have the coordinate point 2, 7. And then I'm going to resist the urge to play connect the dots because you don't connect sequences. They're just dots. Now typically for a sequence, you're going to want 4 coordinate points. The reason I didn't have us do a 4th coordinate point of 3 is because I did this problem before, and that's 10, and it's off the graph. But you can continually use this sequence to build more terms in your sequence as you go. Bless you. Our first goal today is to make sure we can recognize arithmetic sequences. The thing about arithmetic sequences, again, is that they change at a constant rate. So if I looked at the change in these outputs, each time, how much did these go up by? 3. So we want to look at the numbers in my sequence, the values in my sequence, and make sure that they're changing at a constant rate or have that common difference. So let's do that in these 4 examples down here, but we're actually going to start with C and D. I want to do these first. Okay. Normally, a sequence of numbers is a list of numbers in a particular order. So this is a proper way to write a sequence, where we would say the 0th term, or the first term in the sequence is -7, and then -2, and then 3, and then 8, and then 13. So we have a list of numbers, right? Let's see what the difference in these numbers are. How do I go from -7 to -2? How about from -2 to 3? And then 3 to 8? Oh, keep going. Since we have the same number in my sequence for the common difference each time, we can say that, yes, this is an arithmetic sequence because we have a common difference, and that common difference is the number 5 because it's changing by 5 each time. It's pattern recognition, essentially, but made fancy with all this notation. Can we do the same thing for D? How do I go from 1 to -2? How about from -2 to 3? Yeah. Oh, full stop. Does this look like it's going to be arithmetic? No. No, because it's not consistently the same number. Now, I'm a nervous kind of person, so I'm always going to actually check and make sure that it somehow I didn't get this wrong and just had to, all the rest of them are saying, I'm like, well, I just added wrong. I check everything. Now, but this one is just not arithmetic because arithmetic sequences have that common difference. They have a constant rate of change. Okay, but let's see if they give you a sequence in sequence form. So this is S sub n. It's called S because I don't know if it's an arithmetic sequence. That's why we were using A sub n earlier. This is just a sequence, so S. We're trying to determine if it's an arithmetic sequence. So we build a table of values to check the change in the values. So I'm going to have n, and I'm going to have S sub n, it's like x's and y's, and I'm going to plug in 0, 1, 2, and 3. If I plug in the number 0, 0 squared minus 3 is what? And then if I plug in 1, 1 squared minus 3, -2. And then 2 squared minus 3, and then 3 squared minus 3, 6. So if I look at these outputs, the actual numbers in my sequence, let's see how these numbers are changing. How do you go from -3 to -2? How about from -2 to 1? 2? Plus 3, and then from 1 to 6. Is this an arithmetic sequence? No. So we would just say not arithmetic. That's what we're checking today. Because arithmetic sequences have a common difference. Can y'all build the table and decide if B is arithmetic or not? And if it is, tell me the common difference. So you do the same thing like we did on A for B. Okay, if you plug in 0 to the sequence, what's the output? 6. If I plug in 1, and then, okay, great. So I'm checking the difference in between these values. This is a -2, and then a -2, and then a -2. What does that mean for me? That this is an arithmetic sequence. And what is the common difference? -2. Cool. Sound good? It's pattern recognition. We've been looking at patterns since like kindergarten. We can do this. The only way that it's going to be made harder is if it's going to be questions like that are on the back page. It's still a pattern that we're working with. You just have to now use the formulas. So it says, let A sub n be an arithmetic sequence with A sub 3 equal to 8 and D equal to -3. Part 1 is to write an expression for A sub n and then use that expression to find A sub 12. Okay? Just because it's on the other side of the paper, I want you to write this down for a second, like as a little side note. When we're working with sequences, you do want to think about the point slope formula, because it's a lot easier to remember the sequence version if we use point slope. And if some of you are all like, that's not like point slope because it's y minus y1 equal to m times, yeah, you're right. I just moved the y1 to the other side, so it's solved for y. If we change it from point slope form to sequence notation, this would be A sub n equal to some other value in the sequence, A sub k, plus the common difference times n minus the other input value. In point slope form, when you were solving this one, you would have plugged in a number here, here, and here. So guess what numbers we're plugging in? The same 3 spaces. Those are still the important values that we're going to use in this formula, just like we did with a linear function. It's just in sequence notation, so it uses different letters. So let's figure out what all of those things are. Well, obviously, what is the common difference here? -3. So that part's easy. I know that this is going to go where the D goes. Now, what about the K and the A sub K? 3, yes, not 12. It's going to come from this. If this was written as A sub K equal to some value, equal to some value, right? What is K? 3. And what is A sub K? 8. I have the 2 numbers that I'm using. It's still like an input and an output. The input is the subscript. The output is what it's equal to. Okay? So if I was using this and plugging it into my formula, I would say A sub n is equal to A sub 3 plus -3 times n minus 3. Yeah, we're going to substitute one more thing. What is A sub 3? 8. So you do want to make sure that you're actually substituting the values in. This is our notes. I want to make sure you know where these numbers are coming from. A sub 3 is 8. So we would put 8 in that location. And then just because I can't help myself, there's all these numbers, but I'm desperate to do some math after fall break. And look, I can distribute this. This becomes 8 minus 3n plus 9. And then I have 8 plus 9. Oh, those are regular numbers. My formula for A sub n for this arithmetic sequence is going to be 17 minus 3n. Did I have to do that? No, I just couldn't help myself. You could have stopped here. That is a formula, but chances are it's not going to be an answer choice, so you will have to reduce your answer choices. Yes, now we have to keep going. It also asks me to find A sub 12. What does A sub 12 ask me to do? Like, what is this asking? Plug in what? 12. Very good. It wants the 12th term in the sequence. So to plug in 12 is to find the 12th term in this sequence. So if we do that, this is going to be 17 minus 36. And if we turn our brains on this early Monday morning, that's negative 19. And voila. So we can use the information we were given, just like with a point and a slope, to find the equation for the sequence and to use the equation to predict the future, to predict further values in the sequence. Can I make it just a teeny weeny bit harder? Yeah, I'm going to do it anyways. Thank you for your honesty. Okay, in example 4, it says let a sub n be an arithmetic sequence. This time, the information it gives us is a sub 2 equal to 7 and a sub 6 equal to 9. So did they tell us the common difference? We're going to have to find it. Not a big deal. We're capable. But we're going to write an expression for a sub n and then use the expression to find a sub 24. Cool. Here's what I know about sequences. I know that they have an equation that is a sub n equal to a sub k plus d times n minus k. What is the one thing that I know that I'm going to need to write for this formula? Yeah, I need a k, but more importantly, I need to know the common difference of this formula. This is what I don't know. And I have 2 coordinate points technically from the information that was given. If I was given a sub 2 equal to 7 and a sub 6 equal to 9, I can plug those things in as a sub k and as a sub n. I just wrote that backwards. A sub n and a sub k. Meaning, I will do the following. I will say a sub 2 is equal to a sub 6 plus that common difference that I don't know times 2 minus 6. N, right, the location of n, both of them are 2's. Where k was, both of them are 6's. But a sub 2 is equal to 7 and a sub 6 is equal to 9. So if I start to solve this, 2 minus 6 is negative 4. I'm just solving for this one missing piece of information. Subtract 9 from both sides, you end up with negative 2 equal to negative 4 times d. What do I do to solve for d? Divide by negative 4. So negative 2 divided by negative 4, that's positive 1/2. So we have the common difference. Awesome. Now we can use that common difference to write our formula. It does not matter whether you use a sub n or a sub k in your formula, but since we already put a sub 6 in that location, we're just going to stick with that. So we go back to the original formula, and we're going to fill this in. But we're going to leave the a sub n and the n as those letters, like x's and y's. So this is going to be a sub 6 plus 1/2 times n minus 6. Putting the n's back. But we know a sub 6 is 9, so this is 9 plus 1/2 times n minus 6. And since this is just a linear equation, we can't help ourselves. We're going to go ahead and distribute that 1/2, where this would become 9 plus 1/2 n minus 3, because 6 times 1/2 is 3. I have 2 like terms in the 9 and the negative 3, so my formula for a sub n is 6 plus 1/2 n. But this question also asks me to do what? Plug in what? A sub 24. Make sure you say sub because it's a subscript. A sub 24. Very good. So we're going to do 6 plus 1/2 times 24. Well, 1/2 of 24 is 12, and 6 plus 12 is 18. So a sub 24 is 18. What if I want the same sort of thing where I want you to write an equation for me and use it to predict another value, but I don't give you the information in words, I give you this graph. It says several terms of the arithmetic sequence a sub n are shown above. Find an expression for a sub n and use the expression to find a sub 17. Okay, first things first, let's make sure we read this graph appropriately so we know the information that it gives us. This coordinate point right here is what input value? What output value? 8. So this is a sub 0 equal to 8. What about this coordinate point? How would you write that one? A sub 1 equal to 6. Okay, what about this coordinate point? Okay, and then this last one down here. Cool. Now that I see this, and like we could probably see all of this without writing this information, how are these numbers, how are these outputs in this sequence changing each time? -2. So that tells me that the common difference here is going to be -2. I can see that from the graph. I can see it from the change in my output values when I write them as coordinates, as sequence coordinates. So we can use that information to write an expression. Now we already have the common difference and we already have a coordinate point, so we can just jump right in. Again, because these are our notes, let's just start by writing that sequence formula one more time. A sub n equal to a sub k plus d times n minus k, because we got to get that formula in our brain. It's point slope form adjusted. It does not matter which coordinate point you use. So for fun, we're going to use a sub 3. So we have a sub 3 plus -2 times n minus 3. Why did I pick a sub 3? Because I felt like it, honestly. 3 is my favorite number. What is a sub 3 though? We already wrote it down. 2. So if I plug a 2 in here, this is going to be 2 minus 2 times n minus 3. We distribute. This is 2 minus 2n plus 6. We combine our like terms in the 2 and the 6, and we get that our formula is a sub n equal to 8 minus 2n. Now we just actually did a whole lot of work that we didn't need to, and I don't want you to write this next bit down. I just want you to watch the screen for a second. There was a second formula that I haven't been using because it's only used when you have an initial value, where it says a sub n is equal to a sub 0 plus dn. This was the point slope or the slope intercept form version when we have an initial value. But y'all, what was our initial value? What was a sub 0? 8. What was our common difference? So I could have just done this. Oh my gosh, look at that. Okay, only a few times will you be given the a sub 0 term to take this shortcut. You can. I would just rather get used to using the point slope version of this so that if you're not given the initial value, that you can still do the problem. Does that make sense? So if you notice you have the initial value, you can use the initial value for this shortcut, but you eventually get the same answer anyways. So it doesn't really change things. I'd rather use the one that works every time. Now this does have a second part of this problem. It says to use the expression to find a sub 17. So all I'm doing here is I'm plugging 17 into either formula because they're the same. 8 minus 2 times 17. Well, 2 times 17 is 34. And 8 minus 34, that's negative 26. Is that right? Yes. So a sub 17 is negative 26. Questions, comments, concerns about arithmetic sequences? Pretty simple, right? It's just pattern recognition, changing by common difference, easy peasy lemon squeezy, linear functions. Yes? Cool. There's a second type of sequence we're going to deal with today, and this is our transition to Unit 2, is working with what are called geometric sequences. Geometric sequences do not have a common difference. They do not change by the same value each time, by adding or subtracting. For geometric sequences, they're going to behave like exponential functions. Does anyone remember like anything about an exponential function from when you learned about this in Algebra 1 and 2? No, that's okay. They're the graphs that grow or decay. Do those words sound familiar? Yeah, this is going to lead us into Unit 2 talking about exponential functions. But these sequences behave like exponential functions, meaning they don't have a common difference. They have what's called a common ratio, or a proportional change amongst their outputs. In layman's terms, that means you are going to be multiplying or dividing, which is multiplying by a fraction, numbers each time instead of adding and subtracting. They're going to be multiplying by the same number each time. Now again, that's multiplying potentially by a fraction, which feels like dividing. It's like adding a negative number or subtracting. You get it. There are, again, two formulas that we would have for geometric sequences. The first one is G sub n equal to G sub 0 times r to the n power. Notice I've changed from using A sub n's for arithmetic sequences to G sub n's for geometric sequences. Huge hint for you on what kind you're using. Now we're going to use that one just like in the arithmetic sequences if we have the initial value. That's sub 0. That's basically your y-intercept. It is your y-intercept. But if you don't have your y-intercept, the other formula you're going to use is G sub n equal to G sub k times r to the n minus k. It's not called point slope because it's not a point, it's not a slope, it's a different kind of function that doesn't have slopes. But you can think of this like the point slope version of the regular initial value, because in the formulas, the r stands for the common ratio. And the G sub k is any like coordinate point called the kth term in the sequence. But basically just another coordinate point, the same way it was another coordinate point in the first part. Okay, so for geometric sequences, they're not changing by addition and subtraction, they're changing by multiplication and division, which is the biggest difference between arithmetic and geometric sequences. Let's see what one looks like, and we're going to have to start remembering how to do exponents in our head. It'll be fine, we can do it. So if we're doing the same thing, we're going to graph G sub n equal to 8 times 1/2 n. The way we did this a second ago was to make a table of values of n and G sub n's. And I'm going to do the three numbers 0, 1, 2, and 3. Remember, we're not plugging in fractions. These are just whole numbers because they're just dots on the screen. So I'm going to be computing 8 times 1/2 to the 0 power. And here's where we need to start remembering some exponent rules. What is anything to the 0 power? So 8 times 1 is?
8.
What? 8. Yes.
8 times.
Yeah. Cool. Let's do 8 times 1/2 to the first power. What is anything to the first power? Itself. So 8 times 1/2, which is 8 divided by 2, 4. Then we have 8 times 1/2 squared. A rule with exponents is that if you're squaring a fraction, you square the top, square the bottom separately. So 1 squared is 1, 2 squared is 4. So I'm doing 8 times 1/4, which is 8 divided by 4, 2. Then you have 8 times 1/2 to the third power, and here's the cheat code. What do you notice about all of these output values? They go down by half because we're multiplying by this 1/2 common ratio. So 8, 4, 2, what should be next? 1. That makes sense to me. 1/2 to the third power is 1/8, so 8 times 1/8 is 1. If we graph this, here's what it's going to look like. We have 8, 0, 8. We have 1, 4. We have 2, 2, and we have 3, 1. This is no longer a line that we can connect them with. It would be a curve if we were connecting them, which we're not because this is a sequence. So for geometric sequences, you're looking to identify a common ratio, meaning you're thinking about multiplication and division, not addition and subtraction. Can we see if we identify them correctly first? For C and D, which I know I'm jumping to C and D first, again, this is a sequence of numbers. It's in a particular order. If I was checking to see if this was geometric, I'm going to check multiplication and division. Using multiplication and division, how do I go from 1 to 3? Times what? 3. Okay. How do I go from 3 to 2 using multiplication? It's times 2/3, but yes, times a fraction to get smaller. Okay, automatically. Are those the same numbers? No. And if I was just looking here, I would go back to times 3, and then I would go back to 2/3. Like, it's not consistently the same number each time. So this sequence is not geometric. Not geometric. It is still a sequence. There's a pattern here. It's just not a geometric sequence. Now let's check D. If I'm trying to go from 16 to -8, what do I have to multiply by? -1/2, -0.5. How about from -8 to +4? Times -1/2. How about from 4 to -2? And then -2 to 1. So each time I'm consistently multiplying by -1/2. That means for me that this is a geometric sequence and that the common ratio is -1/2. That's what I'm multiplying by. I'm dividing by -2, yeah? That's what I'm multiplying by each time in this sequence. Let's check A and B here. So these are the ones where we need to get some values in my sequence to see how they're changing. So if we have n and we have s sub n, 0, 1, 2, and 3. If we're plugging in 0 to this function, what is 3 times 0 squared? Let me back up. What is 0 squared? Times 3 is 0. Okay, then we plug in 1. What is 1 squared? Times 3. 2 squared times 3. And then 3 squared. 9 times 3. 27. Ooh, fall break did us in, didn't it? Same. Okay, if I look at the difference here, again, I'm trying to use multiplication and division. It's not arithmetic that we're checking for. We're checking for geometric. Is there any way I can multiply and divide anything to go from 0 to 3? No, because anything times 0 is 0. So, like, we can't even do this. This is just definitely, like, not geometric. The end. Let's check the other one and practice our exponent skills. I'm going to do this one with you. So if we have n and we have s sub n, this is a sequence. We're trying to determine if it's geometric. We're still going to plug in 0, 1, 2, and 3. If I plug in 0, this is 4 times 2 to the 0 minus 1. What's 0 minus 1? What's anything to a -1 power? Ooh, do we remember that one? Flip it. Yes, it becomes its reciprocal. So instead of 2, this becomes 1/2. What's 2 times a half? 4 times a half. 2. All right. Okay, let's try another one. Let's see if we got this. 4 times 2 to the 1 minus 1. What's 1 minus 1? What's anything to the 0 power? So 4 times 1 is 4. All right. If we're plugging in 2, 2 minus 1 is 1. 2 to the first power is 2. And 4 times 2 is 8. Three minus 1 is 2. What's 2 squared? 4. And then 4 times 4? 16. So if I'm looking at these output values here, how are they changing with multiplication and division? Multiplying by 2 each time. Very good. So we would conclude that this is a geometric sequence and that the common ratio is 2. Jumping into a problem like we did for arithmetic, because these kinds of questions can come in either form. Let G sub n be a geometric sequence with G sub 1 being equal to 12 and R equal to 2. Find an expression for G sub n and use the expression to find G sub 4. Okay, again, I want to write down the formula. It's actually on this page, but just so it's exactly where we need it. We are filling in G sub n equal to G sub k, parentheses r to the n minus k power. We have everything we need here. And what's nice about geometric is we don't have to do any of the like distribution and reducing. You just plug it in, you're done. Because we haven't learned the skills to do the simplifying yet. We will. Wait for 2.4. But if we plug in what we know that we have this value G sub 1 equal to 12. So I can plug in the value G sub 1, the common ratio, and the number 1. But what is the value of G sub 1? 12. So this is 12 times 2 to the n minus 1, and we're done. Again, I wrote a lot of extra work on here. You probably won't need to do when you're doing this problem, but these are our notes. We want to make sure we're writing enough so we look back and we're like, oh, I know what I did here. But we have this formula. We don't have to do any reducing yet. We haven't learned the skills for that quite yet. But we can use it to produce some outputs here. And we're trying to find G sub 4. So if I want to know G sub 4, it tells me to plug what number into this formula? 4. Easy peasy, we can do that. We just have to remember our exponent rules. G sub 4 would be 12 times 2 to the 4 minus 1. What's 4 minus 1? What's 2 cubed? Don't say 6. Thank you, 8. And then 12 times 8? Ooh. 96. Again, just because these are our notes, let me show you a little bit of work here. So if you got lost in what I said out loud, G sub 4 is 96. But I showed my work. Okay, last one. Same vibe though, we're going to have a graph and we're going to need to write a sequence from this graph. So let's do like we did on the front page and let's just list out the information we have. This coordinate point is what? G sub 0 equal to? Very good. What about this one? Okay, keep going. Equal to 2. And just because I can't really fit any more after this, we'll just do this one as the last one. G sub 3 equal to? What are happening with the output values? What's happening each time? They're halving each time, which means that the common ratio is 1/2. We're dividing by 2 or multiplying by 1/2 each time. Okay, again, it doesn't really matter which one you choose, but because I'm in charge, we're going to use my favorite number again. So we're going to use G sub 3 to write our formula. So if I write down the formula itself, we're doing G sub n equal to G sub k times r to the n minus k. That's what we're filling in. We'll get there. You're talking about G sub 0? Yes. So if I plug in G sub 3, because I like 2, 3 is my favorite number, and I plug in my common ratio, which we found to be 1/2, I would have G sub 3 times 1/2 to the n minus 3, or 1 times 1/2 to the n minus 3. Now again, kind of like, I think this is what Nick was talking about. We could have totally used the initial value version of this since we know the initial value, which means we would be plugging in G sub n equal to G sub 0 times r to the n power, which is 8 times 1/2 to the n. But right now, we don't have the skills to verify that those are the same formulas. We will eventually learn those skills and how those are equivalent, but not until 2.4. So we'll get there. You can use any coordinate point that you have. We just can't verify that they're all the same just yet. We'll get there. But this problem did want me to find G sub 10, which again, what is that asking me to do after I write my formula? Plug in 10. So if I do G sub 10, I would do 1 times 1/2 to the 10 minus 3. What's 10 minus 3? 7. Let's flex our math muscles here a second. When you're raising a fraction to a power, you can do tops by itself and then bottoms. So 1 to the 7th power is what? What's 2 to the 7th power? Let's walk through it together. 2 times 2 is? Times 2, times 2, times 2, times 2. times 2? 128. So this is 1 over 128. And 1 times 1 over 128 is just 1 over 128. Woo-wee. Good job. Look at that, flexing your math muscles. That would be a question I would hope would be on the calculator section of a test, but here we are. It probably won't be.
You sit there for 5 minutes working out.
It's just a multiplying 2 to the 7th power. Okay, are there any major questions before we switch to some PSAT prep? No? Okay, fabulous.